Good morning. This is the video for the next part of section 4.4, where as you can see, we're looking at what's called the mean value theorem for integrals, and then we're going to talk about the average value of a function. And I will warn you, for both of these things, neither of them are that difficult, but both of them, if you're not careful, you'll think of the wrong thing. So that's what I encourage you to pay attention to as I do this. So first thing says mean value theorem for integrals. That phrase, the mean value theorem, should ring a bell. We did a mean value theorem back in chapter, I don't know, 3 maybe. It said this, and this is not what we're doing today, but this is the mean value theorem said that there's some, as long as the function is differentiable, that there's a point in the middle between A and B such that f prime of C is f of B minus f of A over B minus A. And remember, that sounded more confusing than it was. That just meant there's A over there and B over there. That if the function is continuous and differentiable, whatever the slope of the secant line is, which is this red line right there, which is like that part of the formula, that's just y2 minus y1 over x2 minus x1, that somewhere, there happen to be two on my picture, somewhere there's a point C where the slope of the tangent equals the slope of the secant. That was the mean value theorem. That's a derivative thing. Now we're talking about integrals, antiderivatives. And so now we have the mean value theorem for integrals, which says this. All right. It says, my picture keeps getting in the way. It says if f is continuous on the interval from A to B, then there exists a number C such that, and I've got this big equation here. Let me make sense of this. The left side says the integral from A to B of f of x dx. Well, that's what we've been learning this chapter. That represents the actual area under the curve. So this side of the equation, integral from A to B, so like this picture up here, that's just the whatever this actual area is, which thanks to the fundamental theorem of calculus, we can now calculate. This theorem says, the mean value theorem says that there's some point C such that the actual area, which is that thing on the left, equals this quantity here, f of C times B minus A. And I need to convince you that that's a formula you've known for years. F of C times B minus A. Let's look at the picture. F of C is this distance right here, and B minus A is this distance right there. We are literally finding the area of a rectangle. So no matter what the actual area is, somewhere in the interval, there's this value C, that if I just go up from C to the function, which is this height right here, and I find this rectangle, which I did in blue, that the area of the rectangle equals the actual area. The mean value theorem just says that it's an existence theorem, that there has to be a number between A and B such that the area of the rectangle equals the actual area. And one of the things you'll be asked to do with this, which I think the first example does, is to use the mean value theorem for integrals to find that value C. Like, what number is it between A and B such that the actual area under the curve, which is the left side of the equation, would equal the area of the rectangle. So that's this first example. And your homework assignment tonight has two sets of problems, or two types of problems. The first one looks like this. It says, if I can, there we go. It says, find the values of C guaranteed by the mean value theorem for integrals. Nice little typo there. The mean value theorem for integrals, okay? For the function over the given interval. So I have a function, f of x equals x cubed. Notice I didn't even draw the picture. I guess I could have, but I didn't. And it gives you the interval from 0 to 3. So the first thing we have to do, again, I'm going to kind of scroll back and forth in the theory. First thing I'm going to do is I am going to actually calculate the actual integral from A to B. Like, I'm doing this part here. Like, let's find the actual area under the curve, which will still be negative below the x-axis. Really, it's the integral at the area, but let's find the integral. So that's what we've just been doing for. So this process here has been what we did. So to take the integral from 0 to 3, I took the antiderivative of x cubed, which is x to the 4th over 4, and I'm going to evaluate it. I forgot my evaluate it from 0 to 3. And then remember what that means. I'm evaluating at, change colors here, I'm evaluating it at 3 minus evaluating it at 0. So it's capital F of B minus capital F of A. Turns out to be 81/4. And again, that's the kind of problem we just did in the first section 4 assignment. So that means the actual area under the curve is 81/4. And actually, a little sketch of this picture might actually help the cause. So let me just draw this. This is x cubed, kind of looks like that. So we'll call this 3 here. So this region right here, which I will color in green, the actual area, which is that, is 81/4. Now, what the mean value theorem says is somewhere in here, I don't know where, somewhere we'll call it about there. Oh, let's change colors. Somewhere there's a value c. So if I go up to the function here, that this rectangle would have, it's supposed to be a rectangle, forgive my drawing, would have the same area as the actual area, which is 81/4. So we found the actual integral from a to b was 81/4. And what we're going to do with that is we are going to set, notice this right here. That's the other half of that theorem. F of c times b minus a. Remember, that's the height of a rectangle times the width of a rectangle. We're going to set that equal to, in this case, 81/4, and solve for c. So this f of c, that's just my actual function, which was x cubed, but I'm going to write it as c cubed, just because I'm trying to solve for c. And then b minus a here, that's just 3 minus 0. So that's the height of a rectangle times the width of a rectangle. And we're setting that equal to 81/4. And now it's just doing some algebra carefully. Let's see, 3 minus 0 is 3. If I multiply by a third, I get c cubed is 81/12. I reduce that to 27/4. And then I just cube rooted that, which in this case does turn out to be a crazy decimal of 1.889. You could have, without a calculator, you could have left that as the cube root of 27/4. So that means if I go back up to my picture, that this number right here, this c value right there, that c value is at 1.889, where the height of the function at that c value times the interval, that area of that rectangle is the same as the actual area. So the mean value theorem is really, again, it's just what's called an existence theorem. It proves that there must be a value c such that the area of the rectangle equals the area of the actual area under the curve. Now, the second result, which is extremely related to this, is much more important in that we'll use it much more. And you'll see in a minute how this all ties together. The second thing we're learning today is what's called the average value of a function. And again, I have here a very important warning. That is not the average rate of change. Be real careful what the question asks. If the question asks for the average rate of change of a function, well, you've been doing that since about the 7th grade. That's just find the slope of the secant line. The average rate of change, that's the slope. y2 minus y1 over x2 minus x1. That is not this. The average value of the function is, well, let's look at this formula and see how it all ties together. Here's the formula. And this formula you absolutely need to know. The average value of a function is 1 over b minus a times integral from a to b of f of x dx. And that sounds more confusing than it is. Let me go back to my mean value theorem, and I'm going to compare it to this. 1 over b minus a times the integral. So there's, no, where'd it go? There it is. There's my theorem. I want you to notice that this theorem, which I will now make even messier by circling the whole thing in purple, that this theorem, if I divide both sides by b minus a, the left side and the right side, I do in fact get the average value. Like if I divide this by b minus a, the b minus a's are going to cancel. And I divide this by b minus a, I'm going to get 1 over b minus a. So it turns out this, what you're left with is in fact this. The only thing left on the right side is the f of c. It turns out that f of c is the average value. And conceptually, look what f of c was. It is this distance right here. It is the height of the rectangle. The mean value theorem just said there's a value c such that the area of the rectangle equals the actual area. However tall that rectangle is, that's the average value of a function. So if I go back here, the average value of a function, come on, pen, there we go, is 1 over b minus a times the integral from a to b of f of x dx. And then my note says this is f of c. That is the height of the rectangle. So it's really the same theorem. You're doing some of the same math to figure out if you're asked to find the average value. You're just trying to find f of c. Notice you wouldn't have to find where c happens, just what the height of the rectangle is. So Again, I think I have one example here, which looks like this. Now, let me clarify something. This particular example says, find the average value of the function. And that sometimes will be the entire problem. If all it asks is the average value of a function, then, and we'll do this in a minute, we get to our average value, which would be the height of the rectangle, we could stop. This particular question then says, and all values of x in the interval. So then it says, like, at what x value does the rectangle have that height? But not every problem has that part. It might just ask for the average value of the rectangle. So this problem gives us a function. It is f of x equals 3x squared minus 2x. And it gives us an interval from 1 to 4. So let's find the average value of the function. Here, I literally just rewrote the formula for the average value. It's 1 over b minus a times the integral from a to b of f of x dx. And then over here, I just replace it. 1 over b minus a becomes 1 over 4 minus 1. And then the integral from 1 to 4 of the actual function, 3x squared minus 2x. And now we are doing the anti-differentiation fundamental theorem of calculus stuff we've been doing. So from here, this became 1/3, and then the antiderivative of 3x squared is 3x cubed over 3, which is x cubed. And then the antiderivative of 2x is 2x squared over 2, which is just x squared. So this line, notice I still have the 1/3 out front, which is that 1 over b minus a. Don't forget about that. So it's 1/3 times x cubed minus x squared, evaluated from 1 to 4. And then just like we did last week, now I'm evaluating it 4 minus evaluating it 1. So here, this part here is evaluating it 4, and this part here is evaluating it 1. That turns out to be 1/3 of 40 minus 0. Turns out to be 16. That is the average value of that function. Okay. And again, the question maybe could only ask that. This didn't, but it could. So let me show you what I'm doing. Before I finish this question, let me go to Desmos and show you what we've done, what we've done so far. So it's 3x squared minus 2x. Let me go back here. 3x squared minus 2x. Let me show this. And you don't need my kids' quizzes score. Let me just go to Desmos real quick, and I'll explain to you kind of what we just found. As soon as Clever opens up here, sorry about this. It's going to be slow, apparently. It's going to open soon. I feel good about this, but I don't know why. Don't know why it's being so slow. So we're going to try another Desmos talk. We're just going to try and get there a different way. And my internet's being a little slow. I'm in a different room this morning. I blame Mr. Morgan, whose room this is. Okay, this is getting there. Wow. Don't know why this is going so slow. So, okay, there it is. All right. So I just wanted to show you what this picture looks like so we can see what we found. The average value was 16, but it's worth understanding conceptually and visually what that means. All right. My guess is opening up Desmos and having Smart Notes open and having Screencast open, it's making the calculator work harder than it wants to, which is very irritating. I'm going to give this about 5 more seconds, and then I'm going to punt. Oh, it's unresponsive. If that's not a sign, okay, heck with it. Oh, and there it came, and I just closed it. That's how that works. Okay, so let's go back here. All right, so where am I? 3x squared. Sorry about that delay. 3x squared minus 2x. X, 3x minus 2, 3/2. Okay, so that function. All right, so I'm going to do this, and I apologize for this. That function, I think, looks like, let's see, from 1, there's 1, and there's 4. I don't know. I actually think it looks about like this, where it looks like that and that. Well, remember, the integral from 1 to 4 would count this as negative and this as positive. But we found the integral to be 81/4. Yeah, what we just found recently, or when we found the average value to be 16, remember that's the height of the rectangle. So here, there's a rectangle, and that rectangle right there has the area of that rectangle is the same as the integral. So just understand what we found. And then this question then wants us to find x. So it wants us to find like what value is it? Where the height of the rectangle is the average value. So we found the average value. It was 81/4. That's the wrong. That's not the right example. I'm sorry. The average value was 16. Sorry. So now the question is, where does the function equal 16? So you'll notice it says for what values of x does the function equal 16? So we were literally just setting the function equal to 16. We did this in the last example. We set x cubed equal 81/4, and we solved it that way. Now I'm just solving it. Now this happens to be a quadratic. So I set it equal to 0. This happened to factor nicely. If you can't factor this trinomial into this, it's worth remembering how to factor trinomials. And then this turns into two answers, x equals 8/3 and x equals -2. Let me get this thing out of the way. I'm just trying to see some more of my screen here. There we go. Okay. X equals either 8/3 or -2, but in the interval from 1 to 4, -2 is not in the interval, so 8/3. So again, if I go back to my picture, turns out that right there is the value 8/3, which is just less than 3. So that's the x value, where the height of the function at that point is the average value, where the area of the rectangle equals the interval. So again, big picture, what shows up a bunch on my next test and the AP test is just here's something, find the average value of whatever. And so knowing this formula, the average value, which is this formula, integral from 1 over b minus a times the integral from a to b of f of x dx. So having said all that, you have two parts of your assignment. One is just using the mean value theorem to find the value of c. And the second one is finding the average value and finding the values of x. It's all the same theorem. Like you can start with the mean value theorem and get to everything. I would encourage you as you do these to look back at these two examples, because it's easy to kind of lose track of how they're slightly different. So here's the assignment, which is just 328, 50, and 60. That's all I've got for today, which is Monday, March 8th. Tuesday, there's no school because of the ACT. Wednesday, we will do a live lesson. We'll actually be talking about the second part of the fundamental theorem of calculus. So that is Wednesday. So that's all I've got. Enjoy your Monday.